Okay, so we're going to go over today a couple of problems where we are going to be calculating the area between two curves. All right, now we're going to use an integral in both dy and dx. All right, now what I want to show you here that it is possible for any region to, pretty much any region, to calculate, to set up a dy and dx integral. Now, the integrals that result may or may not be able to calculate with the techniques that we've learned so far. All right, so let's start with this example here. All right, it's find the area of the region bounded by the curves y equals to sine of x, y equals cosine of x equals 0, and x equals pi over 4. And I'm going to set up a dy and a dx integral to calculate area. Okay, so first thing we want to start with is, well, let's start with a graph, right? We want to know what this actually looks like, right? So we're going to start by having a graph of the region here. Okay, so we'll graph y equals cosine of x. That looks something like this. All right, we're here, we have 1. All right, and the line x equals 0 is our y-axis, right? So this is x equals 0. All right, and the next graph we'll graph is sine of x. All right, sine of x starts right here, 0, and goes something like that. All right, and the point of intersection is that other intersects with that other line, x equals pi over 4. All right, so this here is pi over 4. All right, along our x-axis, and the y variable, or the value of the y there at the point of intersection is root 2 over 2, right, just from our unit circle. Okay, so now let's identify which region it is that we are trying to calculate the area, right? Is it this one or this one down here? Well, if we wanted to, if we're looking for the region bounded by all of these equations, well, that is this region right here, right? We have x equals 0 here, the graphs of the sine, the cosine, right, and x equals 2 pi over 4. Okay, so we are going to calculate this area here. Okay, so let's start with setting up the easier of the two, that being the dx one, since we already have y equals. Right, now when I try to find or set up these integrals here, I just like to kind of draw, if it's along the, if it's a dx integral, right, I just draw a nice kind of vertical line here, and I just, using my ruler, and I say, all right, at every point along here, the interval between 0 and pi over 4, I always have the same top curve and the bottom curve. All right, so that tells me I'm just going to have one integral to set up. All right, and I also like to draw myself, another color here, just a rectangle there. And since the base is parallel to the x-axis, I'll call it delta x. All right, so that tells me that is dx. All right, so when I set up my integral, here we'll have the integral from 0 to pi over 4. Top curve, which is the cosine of x, minus the bottom curve, which is the sine of x. And that'll be dx. Okay, and then we see here, this is a pretty straightforward integral, right? So if we're asked to do that, I would go ahead and calculate this. Now let's look at how would I set up a dy integral? Right, now if we notice here, so when we flip to dy, right, I'm not going to do a vertical line, but I'm going to do a horizontal line. All right, and if we look here at what happens here, right, remember when it's a dy, it's going to be the right curve minus the left curve. In this case, the left curve is x equals 0. But for the curve on the right, it's not always the same, right? See, at this point, we have that cosine, excuse me, the sine graph. But then at this point, root 2 over 2, it changes. And then becomes a cosine. Okay, so what that is telling me is that, well, if the right curve is going to change, I'm going to need two separate integrals to calculate the area. All right, and the way I'm going to denote that is I'm going to draw two rectangles here. Let me choose a darker color here. This one here, delta y, right? And then one where it changes over to a different curve, delta y here, right? And we can already see what the limits of integration are going to be for these two integrals, right? Along the y, since the dy, we're going to go from 0 to root 2 over 2, and then from root 2 over 2 to 1. Okay, now what equations am I going to use, right? If it's going to be in terms of dy, then I can't use cosine x sine of x, right? I have to solve for x, right? So instead of using y equals sine of x, I solve for x. And in order to do that, we need to introduce an inverse function, inverse of y. And then here, y equals to cosine x. Right, solving for x, we get x equals to cosine inverse of y. All right, so those are going to be the curves that I use, or the equations that I use in my dy integral. Okay, so now let's look at what is that going to look like. All right, so since we do have a change, I know I'm going to have two separate integrals. All right, dy, dy. Okay, so looking at this here, right, the curve on the right is y equals sine of x, but again, I need it in terms of x equals. So the rightmost one is sine inverse of x. The left one is the y-axis, or in this case, 0, so it'll just be that curve. Now the limits, 0 to root 2 over 2. Okay, and then moving on, right, once we're here, we switch over. Right, now what takes over is cosine inverse, oh, excuse me, this should be y. Cosine inverse of y, right, and that starts at where this one left off, root 2 over 2, and it ends at 1. Okay, and again, in both cases, it's minus 0, which is why I didn't write it, right? Technically, it would be minus 0, right? But since it's right minus the left curve, but in this case, we'll just leave it like this. All right, and now notice here that what results, it was easy enough to set it up, but that inverse sign is something that at least at this point in our math education, we haven't gone over how to solve this type of integral, right? So we would go ahead and solve this one. Okay. All right. And that's how you would go about setting up an integral in dy and dx for these two curves. All right, let's do one more example here. All right, and again, here we're going to set up a dy and a dx integral. So it says find the area of the region bounded by the curves y squared equals to 4x and y is equal to 2x minus 4. So again, I'm going to start by generating a graph, right? Whether that be just by hand or Desmos is always a really good tool that'll help us see the graph of these two curves. So let me draw my axes here. All right, y squared equals to 4x. That's a parabola, but it's opening up in this direction here. And y is equal to 2x minus 4 is a line. Crosses the y-axis at -4. has a positive slope, so it looks something like this. Extend these out here. Okay, so let's identify what region it is that we are trying to find the area, right? Now, the region bounded, right? So the bounded area here, as we can see, is going to be this region right here. Right? That is the only region that is bounded by the two curves. The other parts here, they're unbounded. Right? So now the next thing would be as well, what are these points here? Right? So let's find the points of intersection. Okay, so if y squared is equal to 4x, but y is also equal to 2x minus 4, so doing a little substitution here. All right, now we have a nice equation in terms of one variable, and this we can easily solve, right? In terms, we're going to have a quadratic, right? Let's see, expanding this out, we get 4x squared. The outer terms, 2x times negative 4, negative 8x. Inner term, negative 4 times negative times a 2x is another negative 8x, so we get negative 16x. And then the last term is plus 16 equals to 4x. Set this equal to 0. Subtract 4x from both sides. All right, at this point we can use the quadratic formula. We can factor. All right, I'm going to divide by 4 since there's a factor of 4 in each one of these terms. And it makes the number smaller, easier to try to identify if I even can factor this. Equals to 0. We see that's much better, right? Because right away I could see here x minus 4, x minus 1 equals to 0, right? Inner term is, excuse me, inner term is negative, so we get negative x, negative 4x, negative 5x. Outer term, negative, negative, gives me that positive. All right, so that means that we have x equals 4, x equals 1. Right? But these are not points of intersection, right? A point requires an ordered pair, an x and a y. So let's go ahead and find what the y value is, right? Y, I'm going to use, again, y is 2x minus 4. So 2 times 4 minus 4. So that equals to 4. So we have this point here is 4, 4. When x is 1, we get y is 2 times 1 minus 4. That gives me negative 2. All right, so that gives me this point here, 1, negative 2. Okay, all right, so now we have everything we need to start setting up these integrals. Right now for this particular example, I'm gonna do the easier of the two, that being the dy, where I don't have to, I have two separate integrals, right? And how do I know that? Again, I'll take my ruler here. If we're dealing with dy, we have a horizontal. So if we go across this whole interval here, the right curve is always the same. All right. So if we set up our dy integral, we're going to have integral here, and it goes from negative 2, right, the y value, all the way up to 4. All right. And then the right curve is the line. So it's this y equals 2x minus 4, but again, it has to be x equals. So solving for x, we're going to have y plus 4 divided by 2. And I'm going to subtract from that the parabola. In this case, solving for x, we divide both sides by 4. We get y squared over 4. Parentheses here, and then we have dy. Okay, and that would be here, this integral right there. And we have delta y. Okay, so that's how we would set up the dy version. So now let's go ahead and take a look at what would the dx version look like. Okay, so now for the dx, right, one thing, I take my ruler out here and I notice here that we have, all right, well, I have a change in curves here, right? Here, at this point in the interval, the top curve is the top part of the parabola, the bottom curve is the lower part of this parabola. But then after x is equal to 1, that changes, right? The top part is this part of the parabola, and then the bottom part is the linear equation. So we're going to have two separate integrals, right? So right away we could see, and I could already look at, right, for dx, we're going to have from 0 to 1, right, looking at the x values. And then from there, we're going to have from 1, right, all the way up to here, x is equal to 4. All right, and again, it'll be top curve minus bottom curve. Okay, now what is going to be the top curve and the bottom curve? All right, well, here if we have y squared is equal to 4x, solving for y, we get y is equal to plus or minus 2 square root of x. All right, so the top curve is the positive one. And then the bottom one is the negative value. Okay, so for our first one, we'll have 2 root x, top curve, minus the bottom curve, negative 2 root x. All right, so that gets us this part right here. All right, that's delta x. And then in the next part of our interval, that changes. Right, in that part of our integral, the top curve is this root function. So it'll be 2 root x, and then minus 2x minus 4. Okay, watch those parentheses, right? It's going to be minus that whole thing. All right, now in this case, both of these are straightforward enough, except the dx one, it just requires a little more work, but in both cases, it's strictly using the power rule, so it's not too bad. We can evaluate those with the techniques that we've learned up to this point. All right, which one you choose really is up to you. All right, but now we know how to, if asked to set up a dy or a dx, now we know how to approach that problem.